Welcome to the Picture Language Seminar. We're very happy today to have Yury Polyanskiy. He's talking to us from Geneva, where he's visiting for the week. And Yury got his PhD at Princeton 2010. Before that, he was an undergraduate in Moscow, and he's now associate professor at MIT in computer science and electrical engineering. So Yury, you're going to tell us about the uniqueness of the BP fixed point for Ising models. And there are a lot of technical terms. I hope you'll tell us about what they are.
Yeah, thank you, Arthur. Thank you for inviting. Let me share my slides. Okay, so yeah, so when Arthur invited me, I realized this is I thought this is going to be a statistical physics or condensed matter physics kind of group. So that's why I sent the abstract, which sounded very very sort of focused on that audience. But then later Arthur asked me to be more sort of general and then just speak on a higher sort of on a bigger picture. So my talk is more is not so technical, is not as technical as the abstract is saying. So in particular, as Arthur quickly pointed out to me, that even in the title, I'm using the term BP, right, which is not clear what it means. So I'm going to start by explaining what BP actually means.
Éventuellement, il faut téléphoner pour demander si le docteur peut faire quelque chose. Donc, je téléphone à la secrétaire.
I think as a.
Oh. I'm sorry,
Yeah,
I muted you, Yury. I muted the wrong person.
Okay. Yeah, no, yeah. So, okay, that happens. So yeah, but before I start, I wanted to say that the most important part of my talk is that this is a joint work with Qian Yu, who is a postdoc at Princeton, and he's did the lion's share of this work, and he's on the job market also. So that's if you're looking for smart people to join your groups or departments, this is a good opportunity. Okay, so let me start by introducing what BP and what BP fixed point is. So first of all, BP stands for belief propagation, and I will denote and I will introduce this crucial concept of BP operator, which I denote by calligraphic Q. So this is an operator which acts on measures on probability measures. So let me just not rush through this slide and describe it very carefully, because that's somehow the absolutely most important concept for the entire talk. So we take a probability measure mu on reals, and then we sample d independent random variables Ri from this probability measure. So we obtain this Ri, right, R1 to Rd independent copies. Okay, so then we apply certain nonlinearity to it. The nonlinearity is written here. This is f delta function, right? So I'll plot it in a second. Actually, I think my next slide plots this function. This is a function like this. Okay, and so once we apply this nonlinearity to these random variables, we also multiply them by random signs, so which are again IID and coming from Bernoulli delta distribution. So then we sum them up, and we obtain the new variable R, right? So this is a very strange operation, but I will take some time to explain how it arises and why it's important simultaneously in several different domains of statistics and physics and information theory. Okay, so right, so after we did all of this, right, we obtain a new random variable, and the law of this random variable is what we denote by Q mu, right? So this is an operator, right, which takes mu, samples d variables, applies nonlinearity, sums the results with random signs, and the result is a new probability measure, which we denote as Q mu, right? Okay, So now people ask many different questions about this map. And before I state our main result, I wanted to say that this particular version is what we call the basic version in our paper. And there are different variations, such as which are actually more useful for resolving various conjectures in the literature. So sometimes we take the degree D itself to be random, and most often random means Poisson. So instead of sampling the fixed number of terms here, the number of terms is itself random, right? So that's variation number one. And variation number two is when we have some side information, or also known as survey. In this case, after summing these independent terms, we also add another bias term, sort of. So this corresponds to, in Ising model language, this corresponds to some kind of external random fields. Okay, so after we did all of this, right, and this variation, I'm not going to talk about, I mean, these variations in this talk, but the results hold true for them as well. And we still denote the resulting measure by Q mu, right? Okay, so, all right, so now once we define the BP operator, and again, I will restate this multiple times, right? This is our definition. So the main question that we are interested in is in characterizing its fixed points, right? So this is a map from probability measures to probability measures. So we are interested in solving this equation, right? Q mu equals mu. So first of all, let us notice some simple observation. If there is no survey, right? If this term is not present, then because you remember f delta was an odd function, right? So if you set all ri's to be zero, right, and the sum of zeros is zero, so the distribution, which is a delta function centered at zero, is always a fixed point, right, in that case. So in some sense, there's one fixed point which everybody can guess right away, and we call it a trivial fixed point. So that's a not interesting fixed point, not an interesting fixed point. Okay, so what's our main result is actually very simple to state. It says that there exists at most one non-trivial fixed point mu star of this for this fixed point equation. And furthermore, if you start with any non-trivial distribution, then you converge to this fixed point measure. Okay, so that's as I said, that's a if you ever worked on some kind of equations like this, you know that this kind of distributions tend to be very fractal-like, and questions about this fixed point or convergence to fixed point or characterizing fixed points are very, very delicate. So that's why this theorem is was on one hand conjectured, on the other hand, people were not able to prove it for a long time. And on the other hand, if you've never worked with this, you might say, okay, this is some fixed point equation, who cares? And why is it hard, right? So I'll try to answer both of these questions in the slides below. As I said, I mean, this resolves multiple conjectures in the literature. I will touch upon them here and there. So mostly these are conjectures either in machine learning literature. So this is these three references, or in what would be probably should be called information theory questions. Okay, and I should say that these last two papers from 2016 and 2021, they actually did contain some partial results about uniqueness of fixed point, but only for special set of parameters. And at the very end of the talk, if I have time, I will explain why actually authors of those papers themselves were sort of saying that, okay, even though we believe in uniqueness of BP fixed point, we don't know, we have no clue how to prove it, because the methods in those papers were very, very tailored, specifically tailored for this, what's known as high SNR regime. So I'll probably, if I have time, I will try to explain why our proof is completely different from those earlier attempts. Okay, so, but I wanted to start with explaining, you know, for people who are not familiar with this special questions, what is this, how they arise, and also the second my second main goal is to explain how information theory, which is my field of work, right? I'm not a statistical physicist by training, and and you might wonder how come, you know, this like basic statistical physics question, or originating from stat physics literature, right? Why we were able to solve it. So I will try to explain our thought processes, and that's my main goal, just to tell you how this connects to some other stuff in the world of information theory. Okay, so let me describe these three applications in statistical physics, machine learning, and information propagation. And the first application is, or the origin of this kind of equation is in the study of Ising model on a graph, right? So so we consider some fixed undirected graph, and we define probability distribution by it's just a Gibbs distribution, right? It's an exponent of some scaled Hamiltonian, right? Where Hamiltonian simply sums product of spins, right? So we have spin sitting at every vertex, and this kind of distribution favors spins co-aligned, right? If beta is positive, and then of course we have the normalization constant, right? Okay, so this kind of model appears when in statistical learning questions, right? People try to use this model for various correlated phenomena, right, on graphs. And then there is the next key step, right, is that the graphs that appear in nature, right, or in practice, right, they're very complicated, right? So then you have to either sit down and solve, Ising model questions, calculate partition function for one specific graph, right, which is not very illuminating, right? So then what people did, this is the cool idea, right, that instead of thinking about some particular complicated graph, let's think about a random sparse graph, right? And so that's what people did. And they started studying Ising model on random sparse graphs. Now, one thing we need to know is that random sparse graph, right, fixed degree graph, it's logarithmic. If you have n vertices in the graph, then log n depth neighborhood of this graph is actually is a tree with overwhelming probability, right? So that's why if you're interested in studying Ising model or Gibbs measure, right, corresponding to Ising model on a graph, right, you can think of, instead of studying the random graph, right, you can study a tree, right? And then, of course, the complexity. Okay, so that's why, right? So that's how you get to the question of Ising model on trees. But now the problem is that the boundary, right, of the boundary measure on this locally tree-like neighborhood will not be something simple, right? So it will depend on the problem at hand. Okay, but in any case, this is my motivation to start studying Ising model on trees, right? So let's consider a particular version of a graph, which is some tree, say a binary tree, like drawn here. Okay, so now this formula is only defines the probability distribution for finite trees, right? And the question is, how do we extend this definition to infinite trees? Again, for statistical physicists, right, this is a canonical and old question, right, of uniqueness of Gibbs measures on infinite graphs, right? So there are different methods, right? There are different behaviors depending on the temperature, right, in terms of whether there is a unique or non-unique Gibbs measure on the infinite tree, right? And understanding different, understanding different phases or different Gibbs measures on infinite trees also corresponds to issues which arise in finite but locally tree-like graphs, right? Because of the different correlations on the boundary, which are induced by the cycles in the graph. So let's again, this is just a high level, so let's be more concrete, right? So let me start defining. Let me notice that if you're trying to define Gibbs measure on an infinite tree, right? One thing for sure that you can define is a conditional distribution, right? Given the boundary, right? So if you take certain layer, right, and you freeze the spins at that layer, then the conditional probability distribution for the subtree, right, which is supported by these leaves, is just given by the same formula we had before, right? Except now instead of the full infinite sum in the Hamiltonian, right, we only have summation over pairs of vertices which belong to this finite subtree, right? So this is just a conditional measure defined, on a finite subtree of an infinite tree, right? Okay, so now, as usual for statistical physics questions, right, there is two regimes, right? So in the high temperature regime, namely for beta less than 1 over arctange of D, there is only a unique Gibbs measure, right? And this is a very pleasant situation because now if you are in this regime and you're studying random, right, Ising model on a random sparse graph, you could say, okay, if you happen to be in this regime, then there's no question what the local distributions look like, right, in the neighborhoods, because there is only one Gibbs measure, right? Now, once you move in the sort of, let me call it medium temperature regime, right, when beta is bigger than 1 over arctange of D, right, then depending on how you set up these boundary conditions, you can get different Gibbs measures on the tree, right, on an infinite tree, right? For example, I mean, the two distinct Gibbs measures correspond to all plus boundary condition and all minus boundary conditions, right? So in this regime of temperatures, those two measures are not the same. But there are infinitely many other Gibbs measures in this regime. And the question arose, how can we classify or think of these other Gibbs measures? And this is where we need to define the concept of a free boundary Gibbs measure. Okay, so here, this is just like before, right? We consider a finite subtree, and then we define probability distribution without conditioning on the leaves, right? So this is just normalized. We're using the finite Hamiltonian, but we don't normalize we don't freeze the boundary layer, right? So one can show that as the depth of the tree, of this finite tree, goes to infinity, then this sequence of finite measures, right, they converge to the infinite measure, which we call free boundary Gibbs measure, right, on the infinite tree. Okay, so now we have right? So I started by saying that when you're in very high temperature regime, there is only one Gibbs measure. Once you're in the medium temperature regime, there are multiple. So the question is, which one is interesting, right? So I'm saying that let's consider the free boundary Gibbs measure, right, for some reason. I mean, in the questions that I'm going to talk about, this is a natural choice. Okay, so then it turns out that when you go to really low temperature, namely beta bigger than 1 over arctange of square root D, then this measure P infinity is no longer extremal, and it decomposes into a sum of extremal or Bethe measures, right? So that's this is an interesting. So Ising, what I'm trying to say is that Ising model on a tree has two phase transitions. First, as the temperature reduces from infinity, right, you have uniqueness, non-uniqueness phase transition, and then there is extremality of the free boundary measure phase transition, which also is sometimes called spin glass phase transition. And okay, so that's the interesting object for us. Why? Because now, if we could characterize this extremal P alphas, right, then we could get some kind of understanding of this sort of rich variety of Gibbs measures on infinite trees, right? Okay, and the question is how to count these P sub alphas, right? So this is where this cool idea of Mézard and Parisi came about, right? So it's called the one step of replica symmetry breaking. Okay, so what happens, what they suggested is they said the following. They said, okay, if you want to understand this free boundary measure P infinity, here's what you can do. You can first sample the boundary condition YL from the finite measure, right? And then build up from any boundary, right? Using the Gibbs rule, right? You can build up the distribution on the tree above this layer, right? And okay, so do that, and notice that this creates a random distribution on the finite tree, right? Because you first simulated a random choice of the boundary condition, right? And then, given that boundary condition, you simulated a distribution, right? So if you let t go to infinity, then in this way you kind of simulate a random Gibbs measure on a tree, right? On an infinite tree. And Mézard and Parisi had this beautiful physics kind of argument, right? That they said that this random distribution is described by a fixed point of that operation. So of course, I'm not going to derive that how they got here, right? But it turns out that in questions involving sparse locally tree-like graphs, right? If you're trying to characterize the variety of different local distributions that are possible, then that variety, right? So you can count that decomposition of the free boundary measure, right? By knowing the solution to this fixed point equation Q mu equals mu. And this is the first application of our contribution, right? So in some sense, we vindicate this idea of Mézard and Parisi, which is not rigorous, right? So we prove their ansatz, right? We say that indeed, if you're trying to understand this random distribution, right, then you don't, I mean, you're quickly led to these iterations, right? And the key idea is that indeed, because these iterations are convergent to a unique fixed point, right? So then indeed studying this fixed point is no different from it does indeed characterize this random decomposition of the free boundary measure. Okay, so that's sort of the first high-level description, right? So our result says something about counting extremal Gibbs measures on infinite trees, right? But the connection sort of, I mean, it's Mézard and Parisi, right? I mean, Parisi just got Nobel Prize, right? I mean, he's a brilliant guy, right? So sort of the majority of the connection to statistical physics is due to them. We're just solving the analytical question, right? So, okay, but I'm just explaining why Q mu equals mu is such a fun question. Okay, so now here is the second application, which is actually much closer to my field of work. So this is so-called unsupervised clustering problem. Okay, so imagine the following situation. So we have a graph, right? So think of the graph on the left, right? This is what you measure. For example, it could be a social network, right? Or I don't know, maybe proximity measure between two cell phones, right? So you know that, you know, when people happen to share the same cell phone tower, right? And you put an edge between them, right? So you have such a graph, right, at your disposal. And the question is, you want to select dense clusters, right? For example, it could be communities on the social network, right? This could be communities organized by neighborhood or by sharing political views or something like that, right? And you want to convert the graph on the left into a graph on the right, right? So such problems are known as community detection. They are fun statistical inference problems of new type, right? I mean, and they're so fun and so new that sometimes people sort of separate them into a new class of statistical problems known as combinatorial statistics, right? So you observe a graph or you can think of this as adjacency matrix, right? And you try to bring it into approximately block diagonal form, right? By labeling. Okay, so now this is a general kind of picture. There's a very concrete special instance of this, which is known as stochastic block model. Okay, so let me explain it. So a symmetric KSBM with parameters A and B is the following thing. So you have n vertices. Each is assigned a uniformly random color, right? So we take n vertices and we assign n colors, right, from palette of size k. Okay, and now given this assignment, right, this is my planted assignment of communities, right? So I partition people in k communities, and now I build a random graph between them as follows. So for every pair of vertices, u and v, I put an edge independently with probability a over n if they share the same color, right? Or b over n otherwise, right? So if a is bigger than b, then people sharing the same color, right, will be slightly more likely to be connected, right, than people who don't share the same color, right? So this is known as stochastic block model, right? And the goal is to design algorithms, right, which look at the graph and try to go back to this unknown or unobserved random coloring, right? Or, I shouldn't call it random coloring, random labeling, right? Okay, this is the question that for which you can get paid, right, by like social network companies and so on, right, because they really want to do this, right? They want to unhide the truth from their massive observations of graphs. Now, the question that sort of is perhaps more interesting to a scientist, right, is to compute the Shannon entropy of the labels given the graph, right? Because that characterizes somehow, right? So, I mean, I'm explaining to you the question, right? There is some random partitioning of n individuals, right? And you only observe the edges between them, right? Which are very noisy data about them. The question is how much the data you see actually reveals information about what you write about the ground truth, right? So to me, this is a more sort of fundamental question, but you know, say to Facebook, it doesn't matter, right? Because they just want to recover X. It's an algorithmic question that matters. So it turns out our work, again, through the solution to Q mu equals mu, right? The theorem resolves both of these questions. Well, only for K equals 2, I should say, for 2 communities, right? So in terms of the first question, we prove that there exists a polynomial time algorithm recovering X optimally, so as good as non-implementable exponential time complexity algorithm, right? I mean, you could just go and iterate over all possible labels and see which one fits the data best, right? This is an exponential time algorithm. So it turns out you can achieve the same performance using only a very simple belief propagation algorithm. Okay, and the second piece is that we also can compute this complicated posterior entropy in closed form. In closed form up to solving some fixed point equations. Okay, so this is an application, and actually at this point I can smoothly proceed to my third application, and also which will also be the basis of our proof, right? So it turns out that if you look at this problem locally, right, then you notice that, right, that let's say for K equals 2, right, sorry, this should be A plus B over 2, right? So the probability that the average degree, right, of a vertex is going to be what? So it's going to be A over N with sorry, you will sample on average A edges with probability 1/2, right? Because there's N over 2 guys which share the same color as you, right? Or B over 2 edges, right? Because there are N over 2 guys which are of opposite color from you, right? In K equals 2. So the degree is Poisson A plus B over 2, right? And now for 2 vertices which share an edge, the probability that they have the opposing color is actually equal to B over A plus B. Okay? So what I'm trying to explain is that locally, the graph that I see is locally tree-like with this degree distribution, which is Poisson A plus B over 2. Again, this is a typo here, right? And the adjacent spins, right, seem to be correlated like in the Ising model, right? Because the guys which share an edge, right, they're not, if B is less than A plus B, right, they're less likely to share, less likely to disagree, right? Okay, so now this is something known as broadcasting on trees, this problem. So let me describe it. So you can ignore everything I said before, because now I will describe one important application, which will also form the basis for the proof. So this is completely self-contained. So again, you can just sort of tune back and start listening from scratch. Okay, so here is the application 3. So let's fix an infinite-oriented tree, say binary tree, right? And in general, it's going to be d-ary tree. So every vertex can have d offsprings. Okay, so let's sample the root uniformly from plus minus 1, right? So I build this infinite tree and I populate the root with plus minus 1 variable, right? Okay, so now I propagate this label plus minus 1, right, across an edge, but in a noisy fashion, right? When my label plus minus 1 is traveling through the edge, it gets flipped to an opposite sign with probability delta, right? So that's why it's a broadcasting, right? But it's broadcasting across noisy tree, right? So I start with a uniform bit, and when it slides down the edge, it gets flipped with probability delta, right? But it gets copied as well, right? So we copy it twice, and then as it splits here, we get plus minus one with, correlated with this guy, right? And so on. And so we proceed like this sequentially, right? Iteratively, right? Through the root. This creates a joint distribution on a giant tree, right? In this way. And our goal is going to be to reconstruct this label, which we are not allowed to observe, right? Through the labels we see at the bottom layer, right? So again, so we do this iterative strange process, right? Where we copy noisily, we propagate noisily, and then we copy twice, we propagate noisily, copy twice, right? And at the end, we get 2 to the k of the labels, and we try to aggregate this information back to the root to figure out whether the original bit was plus or minus 1, right? To go back to the question I was talking before about, right? So in the community detection or stochastic block model, what you would do is you would first design a very simple algorithm which would somehow label the partitions, right? And then given the knowledge of some noisy knowledge, noisy labeling of bits at level k, right? You try to apply inference procedure to clean it up and get a better estimate of this root variable. Okay, but in any case, this is the problem of broadcasting on trees. I guess if anybody wants to ask a question about broadcasting on trees, it's good to ask it now, because that's going to be crucial for everything else I'm going to say. Let's see. So otherwise, I'll proceed with explaining how it. Okay, so right, so okay, so what, okay, yeah.
There'll be a threshold at which you cannot recover the x0, I suppose. Is that right?
Absolutely, yes. And that threshold is actually well known. Yes, correct. And that threshold exactly corresponds to the spin glass transition for the Ising model on the tree.
Thank you.
Yes, thank you. Okay, so this is what we know, what is known as, oh yeah, and I forgot to say that actually this is not a problem which was, surprisingly, it's not a problem which was conceived to solve the stochastic block model. It's a problem that was actually independently stated by people who study phylogenetic trees, because this is somehow the idea of mutations, right, of gene mutations. And then you observe some sort of set of species at a faraway time, right, in the future, and then you're trying to reconstruct what was happening back before, right? So that's how this model actually occurred first, but then it later got connected to the stochastic block model. Okay, so this is what we call a basic question. When you observe the leaves perfectly, now there is an important variation, which is, oh, sorry, right, sorry. I first wanted to describe how you solve the question of broadcasting on trees, right? So now I will describe a simple algorithm known as belief propagation, which actually resolves, makes the best possible estimate of x00 from the leaves, okay? So again, this root variable x00 is our information source, and it spreads across the tree of what in information theory you call binary symmetric channels, okay? So how do we estimate the root from the leaves? All right, so the standard belief propagation algorithm does the following. It does the optimum inference, right? So here, the optimum procedure is to just compute the log likelihood ratio, right? The logarithm of probability of x00 equal to +1 posterior, right? The ratio of posterior probabilities. Let's denote this log likelihood ratio by the random variable r of k, right? It's random because the layer distribution is random here, right? Okay, so right. Oh, I forgot to say that belief propagation is just a simple, iterative recursion upward, right? So you start with messages here, which are plus or minus infinity, because here you know exactly what each spin is, and then you iteratively compute the posterior the log likelihood ratio for parent nodes, right? And you propagate it like this. So it's a very fast and very efficient algorithm. Okay, so now let me denote by mu sub k, the distribution of R of k, conditioned on, oh, sorry, this is again a typo, conditioned on the root being +1. Okay, I apologize for this typo. So we condition on the root being +1, right? And then this gives this random variable certain law, which we call mu k, right? Okay, so then by this iterative decomposition, right? Because you can grow one more layer here, and represent a depth k tree as a gluing of d depth depth k+1 tree as a composition of d depth k trees, right? So then once you apply this belief propagation recursion, you will find out that the rk+1 is expressed in terms of ri's at the bottom layer by precisely the equation we stated in the first slide, right? So that's why we call it belief propagation operator, right? Because rk+1, the law of the law corresponding to the inference quality for depth k+1 trees can be computed from the depth k tree by applying this the belief propagation recursion. Okay, so right, and then there is some martingale argument which immediately shows that this random variable should converge in distribution to BP fixed point, to some BP fixed point, right? So far, not unique. Okay, so I still didn't describe what we contributed to this question, right? So there is a more important variation. So this was a basic variation, but the more important case is when you don't get to see the leaves exactly, but instead you see them with some noisy, you see them in a noisy fashion, right? So you only get to see the leaves with probability, right? So you observe them flipped with probability tau, right? So this corresponds to, you collect species, for example, you look at the genetic composition, right? And you don't get to exact sequencing, right? But only sequencing, right? So observations which are true with probability 1 minus tau.
Excuse me. So when you say the xk, that is the collection at level k, right? It's all the information you have at level k.
Correct. Yes.
Or one particular one. It's not one particular vertex. It's the whole.
No. Yes. Yeah. Sorry. Yeah. Xk is this vector. Yes.
Yeah. Okay. Yeah. Okay. That's all. That's. Thank you.
Yep. Okay. And all right. So now again, to solve this noisy or robust broadcasting on trees question, you again do belief propagation and you do exactly the same thing. And what you find out is that nothing has changed in the iterations. The only change is the initialization, right? So instead of starting with the delta function at plus infinity corresponding to perfect observations at the bottom, right? You now start with a measure which has two components, right? It's a delta distribution at log 1 minus tau over tau and minus log that. Okay, so this is what we contributed to, right? So people did not know whether in the robust variation, you actually, I mean, it was conjectured but not proven, right? That in the robust variation, actually, the reconstruction quality converges to BP fixed point, right? This is the first claim that there is convergence. This is not clear. There is no martingale argument here. But much more cool fact is that the quality of reconstructing the root from a very deep tree is completely independent of how noisy your observations are at the bottom. So again, let me explain this, right? So if I ask you to guess this beat at the root from, say, depth 100 binary tree, right? And I give you clean observations at the bottom, or I give you observations which are true only with probability 0.51, right? Very, very tinily correlated with the truth, right? Your reconstruction of the root beat is going to be exactly the same. So the probability of error, for example, is going to be exactly the same. And the mutual information is exactly the same. And everything is exactly the same. So that's a very surprising fact, which follows from the unicity of the BP fixed point. Okay, so hopefully I convinced you that that this is an interesting question, which sort of has some funny implications. So let me tell you a little bit about the proof ideas. So to start with the proof ideas, I need to introduce some concepts, which it looks like I need to go a little bit fast. Okay, so first of all, I'll introduce the concept of a channel, which again, for information theorists, the channel is just anything which has an input, which takes some input and produces some random output, right? And a particular case of a random channel is what's known as BSC delta channel, right? It just takes a bit and multiplies it by the random plus minus one Bernoulli delta sign, right? This is what I'm going to call BSC delta. So it's very important to notice that the operation of producing from this single bit x00 this very large collection 2 to the k or d to the k number of correlated bits, right? This is also a BMS, or it's also you can think of it as a channel which has symmetry between plus and minus one input, right? Okay, so so that's what we call WK in this talk, right? This is the tree channel. Okay, so now there is an interesting concept for tree channels, which is known as Blackwell preorder. So back in the 60s, people already asked the question, how do we say that one channel is better than the other? And there is one clean definition, which says that, well, X to Y is certainly a worse channel than X to Z if by getting information from X to Z, right, you can further deteriorate it, for example, add more noise, right, to the observation Z to get something that, you know, that exactly simulates the original X to Y channel, right? So it's clearly, right, if you can degrade it like this, right, your data, if you can add noise to your data, then we say that PY given X channel is worse than PZ given X, right? So that's something interesting. So for example, the depth k+1 tree channel, right, is definitely worse than depth k, right? Because we obtain k+1 observations from k, right? Okay, so now another question is, how do you think of a channel when you're an information theorist? Well, instead of carrying this abstract output alphabet, right, for example, consisting of d to the k bits, like in the tree channel, right, we can just think about log likelihood ratios again. That's a sufficient statistic, right? So any channel can be converted into just observation of this log likelihood ratio. And well, then to describe a channel it's sufficient to just describe the distribution of this log likelihood ratio under both x equals +1 and under x equals -1. But because we postulate the existence of this bijection, right, we require symmetry between the plus input and the minus input, right? You only need one input. You only need one law, which we call mu, right? So this is the law of log likelihood under x equals +1. Okay, so there is some technical note that actually this mu should satisfy certain symmetry condition to actually correspond to some BMS channel, but let's ignore this. So from now on, I will always describe a BMS channel by this box showing mu, right? So what I'm trying to say in this slide is that any complicated binary channel with symmetry between plus and -1 input can be associated to a unique probability distribution on reals, and right, and so and vice versa. Okay, so right, so notice that, for example, in broadcasting on trees, right, we can build the WK+1 channel, right, from WK channels in this form, right? So we start with this binary input symmetric channel, right, which produces from 1 bit 2 to the k bits here, right? And then by copying this construction twice, right, and adding this BSC delta channels, right, this is how we get WK+1 channel, right? That's the iterations here, right? We start with a bit, they propagate through BSC delta channels, and then these resulting noisy copies of X0, right? They propagate through this crazy WK channels, right? And that's the iterative construction. Okay, so that's just a side remark, right? Now we can actually understand this Q mu operation graphically, right? So remember, Q mu was the law of this random sign, right? Okay, so here is how we can represent this BMS Q mu. right? So if these channels are mu's, if we have D channels here, right? D copies, there is D copies here, right? Then this strange operation Q mu corresponds to composing these channels in this fashion, right? So we take D copies of the mu channel, and then we attach to their input, right? Their inputs are bits which are delta correlated to the original bit x0, right? So this is what Q mu is, right? It starts with the BM, this binary channel mu, binary input channel mu, and produces a new binary input channel by taking D copies of mu. Okay, so that's the right. And now notice that in this language, right? So for an information theorist, this is a very natural language, right? So for me, it pains me to describe Q mu operation in this as this formula, even though it's very nice and everybody can understand that, right? But this is the description I like, right? This is something that is very natural to me. And from this description, the fixed point equation Q mu equals mu becomes this infinite divisibility kind of question, right? I'm looking for channels which have this fantastic property that when you take D copies of them and feed them the delta noisy versions of the input bit, you produce exactly the same communication channel as you started with, right? This is kind of infinite divisibility. So it's right. And then our theorem says that there is only one such channel, right? Possible. So that's a really sort of interesting interpretation to me. Okay, so now I wanted to give you some kind of high-level proofs, high-level proof ideas, because I think they will show you just how cool this graphical language is. So first of all, let me mention a key lemma that was used in this field since 2000, and it's due to these four illustrious professors, Evans, Kenyon, Perez, and Schulman. So what they proved is that this channel, which takes a bit, takes a delta, right, flips it with probability delta, and then feeds these two copies, the resulting copy, right, to two different channels mu and nu, right? So this operation, this communication channel, is always worse than if you start with a bit, copy it twice, and then apply noise, and then apply this observation channels mu and nu, right? So in other words, what they proved is that so you lose a lot more information if you first flip the bit, then copy it, right? Then if you first copy it and then flip the bit, flip the two copies independently, right? So it sounds very, very natural, but actually it's not true unless you're in the binary world. That's a surprising fact. So it's not somehow is trivially true. It's a truth which is hard to show. Let me say it. And it relies on the binary alphabet a lot. Okay, so now they used it to prove something that we don't care about in this talk. So let me skip it, right? So, but this is just the general concept, right? Remember, this pre-order means that this is a strictly better channel, or this is a channel whose output can be degraded, right, through some processing to make it simulate this channel, right? Okay, so now our main technical discovery with Qian was the following strengthening of this stringy tree lemma, or STL. So what we noticed is the following, that in fact, right, so if you apply the previous lemma, right, remember that it proves that you can apply it iteratively, right, D times, and then you can prove that this communication channel, right, can be upper bounded by the version without this BSC epsilon, right? You start with a bit, you copy it D times, and then you apply noise D times, right? So this would be a strict, right? So this is just an one-line application of the previous, right, of this lemma of ETPS, right? But what we noticed is that, in fact, not only you can upper bound this original channel by this version, but also by a version with a little epsilon, with a little BSC epsilon inserted here, right? So not only the channel with epsilon equals 0 is better than this one, but also the tiny little epsilon, right? You can still flip, right? In some sense, this is a strict we kind of showed that in stringy tree lemma, this inequality can be made strict. So in a certain sense, right? So this is the main technical discovery, but right. So this is actually, so I mean, this slide is completely rigorous. So it contains the exact statement. So right, it's some nice picture, right? That's why I like to give this talk on the board, right? So it's very easy to state these results on the board, and also, okay, so right, okay, so there is a restriction that you need to have D bigger than 3 copies. For D equals 2 is actually wrong, but there is a fix, which again, let me not talk about it. Right, so let me now mention how this fun picture on this slide implies the main result. This actually only will take me 2 slides. Arthur, I can see you're nervous. Are you expecting me to finish not on time, or is there some time you want me to leave? You're muted, Arthur.
If you finish on time, it's great, but this is really interesting.
Okay. So let me just okay. So let me then go with the proof then, right? So okay. So again, right. So what we prove is that basically when you move this noisy right, so this BSC delta channel, right, when you move it down the edges, right, you can create, right, another BSC epsilon here on top and still result in a better channel, right? Just remember this fact, right? Okay, so now let me, unfortunately I need to introduce one more notation, just because drawing this B phi is a little bit painful with figures. So, okay, so B phi mu will correspond to a measure. So phi is just a scalar parameter, right? So it's just a real number between 0 and 1. So B phi mu is just a convex combination between measure mu and its flip on the minus sign, right? So flip across the 0 axis. Okay, so I mean, in the channel language, this is nothing else than the result of using the mu channel, but when you feed to it the phi noisy version of the binary bit, right? So that's just what I'm saying by this equation. Okay, so now let's define a concept which we called a degradation index, right? So this is the smallest phi. So if you consider you take 2 measures, right? Two different mu and nu, and to them there corresponds a channel, right? As we agreed, right? To every measure we can define a communication channel, right? A binary input communication channel, right? So if mu channel turns out to be better than the nu channel, or worse than the nu channel, I'm sorry, right? Then we set phi to be 0, right? Otherwise we say, okay, so how much noise should I add to the input of mu so that it becomes worse than nu, right? This is the idea of this degradation index, right? It's the least amount of noise needed to make mu worse than nu, right? And again, this value will be 0 if mu is already worse than nu, right? Okay, now, if it happens that phi star, this infimum, is bigger than 0, then as I will show in the next slide, it turns out that our technical result implies that for some epsilon, B phi epsilon Q mu is going to be dominated by B epsilon Q nu, right? So again, so don't sort of don't try to mentally prove this. I will show this implication in a second, right? For now, just trust me that this holds, right? So there's some kind of partial order relationship between Q mu and Q nu defined like this, okay? But now you see if mu and nu are themselves 2 fixed points, right? If mu and nu are 2 fixed points, then Q mu equals mu, Q nu equals nu, right? So then we get B phi epsilon mu is upper bounded by B epsilon nu, right? And remember, this is add epsilon noise, right? And this add phi star noise, right? So this means that you can move B epsilon on the other side, right? And show that this means that mu is already worse than nu when you, instead of adding phi epsilon noise, you only add phi epsilon minus epsilon, right? But this violates minimality of phi star, So something is wrong here, right? Because we selected phi star so that that's the minimum amount we need to add to mu to make it worse than nu. But now all of a sudden we prove that phi star minus epsilon is enough, right? So this means the only assumption we did is this one, right? So this means phi epsilon is 0, right? But if phi epsilon is 0, this means mu itself is less than nu. There is some continuity argument here, but it works okay. Just trust me, right? So this means we proved this fascinating implication. We said pick any two fixed points, right? And then they must be related by this partial order, right? So from symmetry, then there should be the other relation as well. And then this implies that nu equals mu, right? So that's the amazingly simple proof here. Of course, I hid all the details in the statement in proving this fact. So let me show you how it gets proven. And again, I mean, I know that there are many brilliant people in the room, but it's probably hard to, get this on the first attempt. But what I wanted to convince you is that the proof is really unusual. It's completely, it's just drawing some boxes and moving some arrows here and there, and somehow you get a very concrete result at the end, right? So, okay, so what we're trying to prove is that if the phi noisy version of mu is less than nu, then there exists some positive epsilon such that this partial order relationship holds. Okay, so here's how you show it, right? So we set. So first of all, this is the graphical representation of the channel corresponding to the left-hand side of this inequality, right? The beat passes through BSC phi, and then is copied d times, passes through BSC deltas, and passes through mu's, right? Okay, so then we get an upper bound from our main implication, right? We can move this phi down the arrows, right? Down this d arrows and create this BSC epsilon on top. Right, so this is our main technical result, right? So we move this BSC phi down, right, and we obtain this inequality. Okay, so I just rewrote that same inequality here, right? We have BSC epsilon phi delta mu, right, on each branch. Okay, well now we use commutativity of these BSCs, right? It doesn't matter if you first flip the bit with phi probability and then delta, or delta then phi, right? You will get exactly the same result, right? So we decompose them like this. That's exactly the same operation, right? This is the quality of transformations. Okay, so again, so far we proved this implication that the left-hand side is upper bounded by this block, right? Now let's focus on this piece. This is BSC phi followed by mu, right? But that's nothing else than what we call B phi mu, right? So this means this block can be replaced by nu, right? So each of these guys can be replaced by nu and produce a further improvement in observations, right? And that's it. This is precisely what is the left-hand side here. Sorry, the right-hand side here, right? So again, I don't expect people to sort of grasp this on the first in the first attempt, but I just wanted to emphasize how, as I said, many smart people thought about this question for a decade and or more, if you count one RSB work. So then, right, and this is very natural and very easy from information theoretic point of view, but not as easy for others. Okay, so let me ignore all the rest and just finish with conclusions that one future work we are interested in is extending this to query models, but we are not there yet. And thank you very much. And you can find the draft of with full details on my homepage. Thanks a lot.
So thank you, Yury. That was a fantastic talk and very appropriate for the picture language seminar because you had your proof in pictures. Fantastic insights into a new set of problems where you've made some substantial progress. It would be very interesting to know the details, and I'm sure that now there'll be a big discussion. So I'm going to unshare your screen so we can see the audience, and people who would like to talk, I hope that you'll turn on your video so we can see you face to face. Are there questions?
Well, I would like to know, this is all done on trees, and you started out with the K-regular graphs. I mean, do you expect some of the phenomenology to remain the same, or is there something different that will happen once you have loops and so forth?
Yeah, so that's actually a very interesting and deep question. So what happens on the regular graphs is still, in some sense, being understood. So so let me first tell you how the high level answer. So we're trying to understand this Gibbs measure, right, on a very complicated graph, right? Now we know that locally it's a tree, right? So then the only question is, how do those correlations on the boundary, right? What kind of version of correlations on the boundary get selected, right, by the loops in the graph? So, okay, so now Mézard and Paris's answer was that they said, okay, well, we don't know which one gets selected, right? But let's try to just, apply some kind of physics intuition, right, to classify all possible boundary conditions, right? And that's how they got this 1RSB solution. And, so their answer is that you take the solution to 1RSB equation. So we prove that there is at most one non-trivial fixed point, right? They say if all the solutions are trivial, right? If there is no non-trivial fixed points, right? Then their claim, right, that on any locally tree-like graph, basically there is no long-range correlations, right? And everything should behave, basically the Gibbs measure should not contain exponentially many humps, right? It should not separate into clusters, right? But once you have non-unique, once you have non-trivial 1RSB fixed points, right? So then their claim is that there indeed will be formation of the Gibbs measure will decompose into exponentially many clusters, right? And what they're trying to describe is number of clusters corresponding to each value of the free entropy, right? Free energy, right? So that's what 1RSB solution describes. So, but now you can ask rigorously, right? Let's take an Ising model, right? Let's say ferromagnetic Ising model, right? On a random deregular graph. Okay, so it turns out that for random deregular graph, if you are in a ferromagnetic regime, then the Gibbs distribution changes from, the unique one, right, when you're in a very high temperature, right? And once you cross the uniqueness phase transition, right, the Gibbs distribution becomes 1/2 mu plus 1/2 mu minus. And that's it. There is nothing. So nothing interesting happens at the spin glass transition for ferromagnetic. But for anti-ferromagnetic case, for Bethe less than, for our language, nothing interesting happens. Nothing changes when,
nothing interesting happens in the ferromagnetic case. Yeah. Yes. And then what happens in the anti-ferromagnetic case? Then what happens?
Yes. So there is some phase transition at the spin glass temperature. So indeed, you have this, deformation into a lot of clusters, right? So, and apparently basically some frustration gets selected, right, at the boundary, which does not get selected in the ferromagnetic case. But this is only known and understood for binary. Like I'm personally very interested in, for example, also random sign version of the Ising model, right, where you have random. So I think nothing is known for this one, or even random external fields. I didn't talk about this, but our work, we also have random external fields of certain kind, but we cannot say anything about the most exciting version, right? Take a random deregular graph, let's say ferromagnetic Ising model, and take epsilon plus minus epsilon external field at each side.
Yes.
So I think nothing is known about this, but you can write 1RSB equation again, right? But our work does not imply anything about that because there is no reduction to broadcasting on trees. And so that's as much as I know. But again, I'm not an expert on this.
Thank you very much. Very, very, very good talk. I enjoyed it.
Yury, did you think about whether your methods could possibly apply to quantum problems rather than classical ones?
Yeah, I'm ashamed to say I did not think about this, even though I'm a physicist in my sort of bachelor degree. But I did not think of that, and I actually don't know much about quantum Ising models. So, yeah, I only ever studied classical Ising models.
Well, it would be very interesting to look at this class of questions because it comes up in quantum information.
Yeah. Agreed.
So are there other questions?
Well, I just have one other question because it's related to something that I've been thinking about. I believe it's related to this. And I mean, you're talking about binary stuff, but in some cases you're interested in phases and things like that. So if I look at, are there analogous things for broadcasting phases on trees? In other words, I have some angle that I want to recover, and I propagate it with some noise, and I want to know to what extent I can recover.
Yeah. So
So this appears in computer vision, for example.
Right. Yeah. So I'm trying to remember. Right. So you just so you say you introduce random phase. Okay. So I think. Yeah, I think this was studied. This is what's known as Q equals infinity case. But they usually study just a uniform distribution, right? So,
yeah.
So what you do, right, is you set. I mean, okay. So the only model I know of this kind which was studied is the following. So when you propagate across the edge, right? So first you start with the root, which is uniform on 0 to 1, right? And then you propagate across the edge, and you set x to be either equal to its parent, or a completely independently chosen new uniform distribution. So this is in some sense natural limit for Potts model to Q equals infinity. And so this was studied, and the phase transition there is actually very, very simple. It's just 1 degree, and it corresponds to uniqueness. So uniqueness and spin glass transition happens, I think, is at the same. But I personally don't know, for example, robust version, or if you have other channels, like for example, right, and this is a very strange channel, right, where if you see at the bottom any two spins, right, which are exactly equal, you know their parent is equal, right, their greatest common ancestor is equal, right, because, right, there is no chance that you would generate, right, two uniform, right, you understand, right? So, but if you had a more sort of realistic noise model on the edges, right? Like, for example, you add a little bit of phase, as you said, right? Let's say we do addition modulo 1. I mean, this is a cool question. I actually have no idea what will happen. I know that my information theoretic methods will prove some bounds on the phase transition. So I can give you right away a number of impossibility results, but I have zero ideas how to analyze BP or even any suboptimal algorithms for the reconstruction of those questions. Right. Again, BP works on a tree, right, and is optimal, but analyzing it is very tough because there's iterative equations.
Well, thank you again, Yury. This was a fantastic talk, and we're very interested in your results and look forward to your coming back to Boston. So
thank you, Arthur. Thanks so much, guys. This was a pleasure. Have a good day.
Great, and see you next week. We'll have Feng Xu. He'll talk about entropy and quantum field theory. Bye-bye. Bye-bye.
Bye all.